Assalamu alaikum. This is the second video of module 1 of EEE 4505. At the last portion of the first video, I discussed about two significant types of error that needs serious discussion. This video is going to be about one of them, that is round of error. In this video, we are going to discuss about round of error. Okay, if we look at the definition of round of error, it says that round of error occurs when a number cannot be represented exactly in a computer due to a limited decimal binary precision, so it gets rounded. Okay, what does it mean? Uh, this type of error occurs because the system doesn't when the system doesn't have enough place to store data, then we have to round it off. How? Okay, let's look at this picture. We have all seen this type of counter in real life. So these counters have only 3 places to store data, and in this system we can store numbers from 000 up to 999, correct? Now let's say in this system we want to store data of that says 1000, but do we have enough place to store this data? I think no, because it has only 3 places. So if we want to store this 1000 into this system, in that case we would have to round 1000 to 999. So in this total scenario, the amount of error we are getting is 1000 minus 999, which is 1, right? So if we encounter such scenario where our system cannot store enough data, and for that reason we have to round the value, and consequently the amount of error we get due to that situation, that is called round of error. Okay, for example, uh, let's look at the career of prominent Bangladeshi batsman Imrul Qais, and we are interested in his runs in tests and average. Okay, if we look at his runs, that is, he has scored 1797 runs, and if we look at the average, he has scored this amount of run in 74 innings. If we divide it by 74, that gives us the average. Okay, why I have brought it up? Because we want to see what type of error or round of error we experience if we want to store these two data into a system. Okay, let us first begin with storing the runs of Mr. Imrul Qais. So as we have seen in our previous slide that he has scored total 1797 runs. So these data or this mathematical term can also be written in this way, that 7 is its unit digit, and in this way we can separately write all these digits and add them up. That would give us the total value of Mr. Imrul Qais's test runs. Okay, now imagine we have a system where we can store 6 digits, and we are asked to store the data or which says the total runs of Imrul Qais's test career. So how can we do that? We would place this data here, 7 here, we would place 9 here, we would place 7 here again, and 1 here, right? And in these two places we will place 0. So that is very simple. So if we are allowed a system where we can store 6 digits, and we have to store the runs of a prominent cricketer like Imrul Qais, then we are good to go. We can store his runs. So up to what amount run we can store in this system? Even if Imrul Qais scored 99,999, no, 9 lakh 99,999 runs, then we would have able to store this amount of run in this system. What if Imul test carrier had this amount of runs? Will our system allow us to store this run into the system? The answer is no. In that case, we would have to round that runs into this, and then we would store this amount of run into our designated system. So in this process, we would encounter round of error. So it is quite evident that if we are asked to store an integer into a system, in that case, how round of error occurs? Okay. And also, the system we are considering here has a base of 10. You have to keep that in mind. To simplify the concept, up until now I have discussed about a system that has a base of 10. Okay. Now let's complicate the system a bit. Let's look at a different scenario. What if we are now asked to store the average of Mr. Imulkas that we found out with this? And like the previous system, we have that 10 based storing system where we are allowed to store 6 digits. So how can we store this amount of this value into the system? Okay. So for integer, we didn't have any problem storing any data into systems, but now we can see some problems arising. So I think by now we have understood how round of error occurs and why round of error occurs, and we have seen some examples for integer. But the problem with the real life scenario is that we won't always have integers in our hand. In real life, the types of number we face are mostly of this order, like the average of Mr. Imul test carrier. Okay. So this type of numbers are called floating point number, and from now on our discussion would be how we can store this type of numbers into a system. If we are given a system that can hold 6 digits like the previous case, and we are now asked to store this type of a number into this system which can hold 6 digits, and I think you can sense that the round of error will be more evident in these cases. Okay. Now let us look at the number we are interested in. This is the test carrier average of Mr. Imulkas. So this number can be written as this. I hope you all will agree. Also, the same number can be written as this also as well. Also, the same number can be written as this as well. Right? Okay. Why we have converted this number into this? Because in most of the cases we would have to deal with these floating point numbers, and we must come to a standardized system to represent these numbers. So, finally the mathematician agreed that we will represent most of the case we will represent the floating point numbers in this way. This has a standard form, and see, we have represented the our designated number into this format as well. Here this part is called m or mantissa. This is the base of the number. Here we are dealing with decimal system, so the base here is 10, and this is called exponent. Okay. That is the basic idea how we will convert any floating point number into the standardized form. Then we will look how we can store this information into any given system. Now at our hand we have a standardized floating point number, and in this number we know the mantissa, we know the value of base, and we know the value of exponent. So now our task is to store these three quantities into a system. Let's assume we have a system that can hold 6 digits like we did for the total test carrier runs of Imulcas. In this system we have allotted 1 digit for storing exponent and 2 digits for storing the base. So now we are left with only 3 digits to store the value of mantissa. Okay. So look here, what is the value of base? The value of base is 10. So these two places are taken up by this thing. What is the exponent here? To represent this particular number, the value of exponent is 2. So this place is also taken up. And now we are left with the value of mantissa. So what, up to which point we can store here? We can store up to this 2, 4, 2. So using this 6 digit decimal system, we can store the average of Mr. Imulcas like this. So we, in this system we are allowed to store only this, only up to this point of his average, but his real average is this. So due to the limitations of our system, we eventually had to round off his average into this, and we could only store up to this value into our system. So now here the round off error is the actual value minus the value we could store. So that is the round off error for this particular case. I hope you have all understood what has been done here. Now let's discuss it in this way. We have a decimal system and it has option to store 8 digits, and in this system we have allotted 2 digit for storing the base, as the base is 10 and we would need 2 digit definitely to store, and we have set 1 digit to say to store the exponent, and we have left 5 digits blank to store the mantissa. Here is a catch. The value of mantissa has to be between this range. So 1 by b means 1 by base. For decimal case, the value of mantissa has to be less than or equal 1 by 10 or 0.1, and the value of mantissa needs to be within the value of 1. Okay. So that means if we are allowed a system of to store floating point numbers of a decimal base that has 8 digits to 8 digit positions to store, in that system we can store mantissas into these 5 positions. So can you guess what is the lowest possible number? What is let us first guess what is the highest possible number we can store in this system. The highest possible number we can store here is definitely 999, and our base is always fixed 10, and the maximum value of exponent we can put here as 9. So this is the maximum value we can store in this system. And if we are asked to store a value which is higher than 999 into 10 to the power 9, in that case our system would round that off into this number, and we will encounter round of error. Now my question is, can you guess what is the lowest possible number we can store in this system? In that case, the value of exponent will be 0, and you would guess that 0, 0, 0, 0, 1. If you have guessed it in this way, then I'm sorry, you have calculated it wrong, because I have stated one condition that you have to maintain this thing if you are storing numbers in this setup. So the value of mantissa cannot be less than 0.1, and to make this happen we must put the value to make that happen we must put the value 1 here. So this is the lowest possible number, or the smallest number we can store in this setup. And anyhow, so the lowest possible number we can store in this system is 0.1 into 10 to the power 0. If we are asked to store 0.05 into this system, we won't be able to do it, because this is the lowest threshold here, and if we are asked to store any number smaller than this, in that case we have to round it off into this, and then we would encounter round off error here. To level things up, let us now think of okay, up until now we have talked about only decimal system, and also we have talked about exponent having only positive values. So you all will agree that we can also store values of we can also store negative values into exponent, right? Okay, so in that case we would have to allow at least 2 digits to store our exponent, one for the sign of the exponent and one for the exact value of the exponent, and for base it would take up 2 places, right? And if that is the case, in that case we would be left with only 4 places to store our mantissa. So now my question to you is that you calculate what is the lowest possible value that can be stored into this system, and what is the highest possible value that can be stored into this system. Let me give you one clue. In this system we can store values of this order: mantissa into 10 to the power minus 9 and mantissa into 10 to the power 9, but the value of mantissa can take up only 4 digits. And the detailed discussion we have had so far should make you clear that why we cannot store all the numbers into a system, or why we face such limitations. Next we will see what happens in actual systems, because the actual system runs in binary setup. So far we have seen systems that are designed with the base 10, but in actual the computers that we use are based on binary system. Now we are interested to see how the system works in case of the base of the number system is set here 2. We have seen how it will work for the base 10. The setup is same. let's assume we have a system that can take 8 bits, and in these 8 bits we have to store floating point numbers that are represented with base 2. Okay, so let's assume we have taken 2 bits for storing the values of exponent. We have taken 1 bit for storing the sign of the exponent, and then we will be left with 5 bits that can take the values of mantissa. Okay. One thing I think I forgot to mention, if we are storing mantissa here, so for decimal cases, these boxes would represent 10 to the power minus 1, 10 to the power minus 2, 10 to the power minus 3, and up to 10 to the power minus 5. For binary case, these boxes would represent 2 to the power minus 1, 2 to the power minus 2, 2 to the power minus 3, and up to here for 2 to the power minus 5. Okay. If this is the setup we are given, so we can see that for storing the values of exponent, we have 2 bits in our hand, and using these 2 bits we can create 4 different combinations. That means the values of exponent can vary from 0 to 3. But here is another catch: we can add sign. We have allocated 1 bit for assigning the sign of exponent, so the values can vary from minus 3 to plus 3. But in real, here using these signs we can also store minus 4. So this is your task to find out how using these 3 bits we can represent minus 4. So I'm stating for a fact that if we have 1 bit assigned for sign of the exponent and 2 bits assigned for the values of exponent, here we can store values from minus 4 to plus 3. Okay. Then we will be left with 5 bits that can store the values of mantissa. So now let us do the drill that we have done before. So what can be the highest value or the maximum valued number that can be stored in the system? So the answer is obvious. The maximum number we can store here is 11111. If we convert it to uh, binary, we know that this means that we will be able to store this is the maximum value we can store, and if we convert it to decimal, that will give us the maximum decimal number that we can store in the system. The other way around, what is the lowest number we can store here? For if you answer it like the one you answered in for decimal case, you would say that we should be able to store this as the lowest possible number in the system, but the answer will be incorrect because we had a condition to be met that the value of mantissa must lie between this range. So here, since we have the value of b here 2, so the value of mantissa must be higher than 0.5 or less than 1. To make that happen, we must ensure that the value set at this box or the most significant bit is 1. That that is 1 into 2 to the power minus 1 or 0.5 in decimal, and if you convert it to this that is 0.5 in binary. So that is the case. Using this type of setup, you can store floating point numbers for binary case, and actually this is how numbers are stored in our our systems that we use in our day-to-day life. As far as I know, using the MATLAB that we use uh, generally has a 64-bit setup. Using that, they store any sort of number. So if you ever try to write anything, let's say 10 into or if in MATLAB, if you try to write anything of this order, let's say 635 into 10 to the power minus 99, that would automatically round it off to 0, because using that system, the lowest possible number that can be stored is higher than this value. So that is why this cannot be converted into the system, and thus it gets rounded off, and MATLAB considers this one as 0. So I hope by now you have understood why round off error occurs, and if it occurs, we can easily calculate the amount of error. So that was the idea of this lecture, to give you uh, the brief insight into why round off error occurs in systems as we use these systems in our day-to-day life. And if that error occurs, then how can you calculate the error? That part is very simple. So the main idea of this lecture was to get you familiarized with this phenomenon. Thank you very much.